Everyone. My name is Juan Guerra, and I'm a graduate student at Yale University, where I work with Marla Jiha on the internal dynamics of dwarf galaxies. And over the past 4 weeks, I've been working with Mika, as well as David Hogg, Adrian, Jessica, and Emily on the data analysis methods that we use in order to study systems like, okay, this disappeared. Like the Milky Way or the satellite dwarf galaxies around the Milky Way, for example. And just to reiterate the question that we've been asking is that we know that these systems are in halos and subhalos. And what we want to understand about them is the distribution of dark matter, or what is the distribution of dark matter. And the reason why we want to know that is because that can give us hints of into the nature of dark matter, whether it's cold, warm, or fuzzy, or whichever your favorite method is. And really the only thing we know about them, about dark matter, is that it interacts gravitationally. And so we can know that for sure that F equals ma, where the force is the gravitational force. And we can relate that to the underlying distribution of dark matter by the negative gradient of the potential. And we can relate that to the density profile via the Poisson equation. And that's good, except that the data that we have are positions and velocities at a single point in time, until I learned that that's not true. But that's almost always true. And so the bad thing about this is that there's no obvious way or even necessary way that the positions and velocities relate to the underlying potential or acceleration. And so we have to do something slightly different. And when you consider the size of these systems and the typical velocities that we measure, we calculate some very simple timescales. And we can see that this system should be well modeled as a collisions fluid. What that means is that I can write down a function f of xv, which is my distribution function. And what that essentially tells me is the probability of finding a star or a number of stars in some volume in phase space. And that obeys the collisions-Boltzmann equation. And with that, I have an equation that relates positions and velocities to the underlying dark matter potential. The second issue that we then run into is that this is a hard equation to solve. And so all of the methods that Mika sort of described, and then I will describe slightly more, is basically just a bunch of tricks that we have in order to solve this equation without actually solving this equation. But all of the methods use this as a starting point. Okay, so before I go into the methods, let me just restate the project goals, which is to understand the data analysis methods that we use in order to constrain the potentials in systems like the Milky Way or dwarf galaxies. And the way that we're going to do this is by writing very simple implementations that we're going to use to study very simple systems. And what we're going to do next is then test all of the assumptions that go, or first of all, learn all the assumptions that go into these models and test how they react when we break them, as well as figure out what type of scaling relationships they have. And by scaling relationships, I mean how well can they recover the dark matter potential when I have 10 stars or 100,000 stars, or what happens when I set the velocity errors to 0, or when I have some unknown selection effect. So those are all questions that we want to answer. And then finally, we want to compare these methods on real data and also on more realistic simulated data like cosmological simulations. And so first, we're going to start with the simple model. And we played with a couple, but the basic one is we considered a isothermal distribution function in a simple harmonic oscillator. And the reason why we're going to do that is because it makes everything easy. So we can make mock data by just drawing positions and velocities from Gaussian, which is one of the easiest things we can do. And we know all the answers because we can calculate the orbits analytically and the actions analytically and the angles analytically. So we know all of the answers beforehand. And so that's going to make things really easy for us. So I'll go over the methods one more time. And essentially, it's genes modeling, Schwarzschild modeling, or we're going to call extended Schwarzschild modeling, orbital roulette, orbital torus imaging, which I'm not going to talk about at all, the virial theorem, of course, and there's also made to measure and spiral stream fitting. And all of these methods have what I'm going to call their philosophy, but it's really just the way that they go about solving the question that we asked. And with that comes a series of pros and cons. And this is also an annoyingly big table that I would like to go really in depth into, but I don't have the time. So I'm just going to focus on two things: genes modeling and the extended Schwarzschild modeling. And yeah, I'll talk about all of these things. So first of all, the genes modeling. This method starts out by taking moments of the collisionless Boltzmann equation. And what that gives us is essentially a set of equations that are analogous to the Navier-Stokes equations in fluid mechanics. But in our very simple one-dimensional potential or system, there it becomes a very simple equation. And we'll go term by term, but what everything means. So mu z is the tracer density. And already here we run into one of the cons of genes modeling, which is that I have to bin my positions in order to calculate the density of the tracers. I also have to bin my data when I calculate the second moment of the distribution function, which is the average VZ squared. And binning always leads to loss of information. And then I do something worse, which is I multiply these two bin quantities, and then I have to numerically take derivatives of those bin quantities. So it can get really bad when you don't have that many stars. And of course, the d phi dc is our acceleration field, or negative over acceleration field. And the pros is that it's really simple. We can just solve for negative d phi dz, and we can recover our harmonic oscillator force law, that's negative kx. And it works really well, at least for small z, where, as we saw before, there are a large number of stars in those bins. And it doesn't do that well in the outer, for large z, where there are very small number of stars in those bins. But we can recover the force law. And just so that you don't think we can only recover simple force laws, I also tried it out for a very unphysical potential law, where I get a really unphysical neo z, and it still recovers the potential where there are a lot of stars. It obviously does really bad at the edge cases. But like I said, we have to bin everything. And to create these fits, I had to use 100,000 stars with 0 errors. And I still don't fully recover the potential law. So that's genes modeling. And next, I'll go into extended Schwarzschild modeling, which is essentially a phase-based method. And what this consists of is writing down my distribution function as a weighted sum of basis functions. And for this example, I'm going to use a set of basis functions that are just step functions. And to really set myself up for success, I'm going to switch from an isothermal distribution function to a step function in action space. And so here in red, I have the basis functions, and what the algorithm sort of ends up being is finding the weights and the potential such that I can best recover the distribution function. So in this modeling scheme, my data is positions and velocities, and I don't have to bin them. So that's already a first good thing. What I instead do is I build a likelihood function by asking what is the probability that some star falls within some basis function. And after I do that, I get a likelihood function, which is going to depend on the weights and the potential. And so to outline exactly, well, not exactly, but a vague outline of the actual procedure is I first pick a potential, then I calculate the probabilities like I talked about in the previous slide, and then I find the weights that maximize my likelihood function. And then I do steps 1 to 3 again for a big set of potentials, which in this case, it's going to be, like Mika said, where I'm just varying the frequency of the oscillator. And here is where it can become, where we get to the cons of this method, where it can become computationally expensive really quickly. And so I can't really put the genes modeling and this method head to head because I can't do this method for 100,000 stars. I can't do it for 1,000 stars, but I can do it for 10 stars. Yeah, but I also can't do genes modeling for 10 stars. I would have like one bin. So yeah, so it works, right? For 10 stars, I go through this procedure and I vary the omega in a set of, in my potential, and I recover that, or I get that the likelihood function peaks at the true value of omega, which is really good for 10 stars. And again, I wouldn't be able to do this with genes modeling at all with 10 stars. There's no good binning scheme for 10 stars. Okay, let's see. And I went through most of the other methods and implemented them as well, but I don't think that I'll have enough time to really go in depth into all of them. So I'll just quickly breeze through all of them. So the third method is classical Schwarzschild modeling, which it's almost exactly the same procedure that I outlined before, except what I do is I build an orbit library, and then I weigh those orbits, and then with those weighed orbits, I calculate observables like the mean velocity or the average value of the velocity squared and the stellar density, and also the distribution of positions and velocities, and I try to find the weights and the potential that best recovers those observables. But like Mika said, the libraries can get really big really quickly, and even this PDF was really big, and it made my computer freeze. And nobody has really done Schwarzschild modeling for the Milky Way, and that's probably due to the fact that your orbit library would have to be massive, and your system has to be integrable. And after Schwarzschild modeling, I implemented orbital roulette, which basically just takes the idea that the distribution function is only a function of actions, and that the angles will be uniformly distributed. But in order to calculate the angles, I have to know the potential. And so if I take a data set of positions and velocities, and I calculate actions and angles in the wrong potential, then I won't get an even distribution of angles. But if I do it in the right potential, I will. So you can come up with a really simple statistic for varying omega such that you get a uniform distribution in angles. And then there's the Vero theorem, which is like really the simplest thing, which just connects the average kinetic energy and the potential energy. But you can do really interesting things with the individual stars in the system, and you can vary the potential or vary the power law and the coefficient in your potential and make the virial theorem work. And for this example on the right, this is for the solar system, and I recover the alpha that is the correct alpha, because here I'm parameterizing the potential as u to the 1 minus alpha. So I recover that the potential is a 1 over r power law. And this doesn't really work for one-dimensional systems, but I did take a mock data set of a dwarf galaxy. And here the NFW potential is not a power law, right? So there's no simple form for the virial theorem, but I can sort of make one up by doing a Taylor expansion of the potential. And I find that it does kind of peak at or all of these lines sort of converge at the right value. And it really shouldn't work, but it does, kind of. But there's no actual information there. It's really just like a party trick. So in summary, right, all of these methods for sure work, but, and they have different ways of tackling the same question. And so they're gonna interact, or they're gonna behave differently when those assumptions are broken, or when various unknown things in the environment could be happening. So the way that we go about, sorry, we go about starting to study that is by asking what things can go wrong. And there's a lot of things that can go wrong. But we can ask one very simple thing is like, what if the stars are not base mixed? And so if you look at the right column, if the stars are not base mixed, then we break Jeans modeling. And even with 100,000 stars and no errors, we can't recover the potential. And I don't have time for this. So we really only got to the second step of our project goals, which is starting to test how these modeling techniques can be broken. And now, next, we're going to go into really all of the scaling relationships. I mean, how they behave when I vary these, and then compare them to real simulations. And we also have to go to spherical. So yeah, thank you. Thank you for another great talk.
Great talk, Juan. So I had a question about the extended Schwarzschild modeling that you showed us. So you have to choose a number of basis elements to basically have f equals sum over ckfk. Mm-hmm. So do you have an idea about what is the optimum number of basis elements? How do you choose that? Is that dependent on the potential that you're looking at? Or?
Yeah, so that is a thing that came up. And essentially, I chose 200 in this case, which was a lot. But if I didn't choose enough, then when I calculated all of the probabilities, they didn't add up to 1 because I wasn't getting enough of the action space in them. So there is a minimum for sure. I don't know about optimum.
So if you try out any more realistic potential, do you expect that to go up, that number?
I would definitely expect for me to have to use a very fine, very fine set of top hat functions, or maybe ultimately a different basis.
Right. Okay. Thank you.
Yeah, I am sort of relaying a question that came up during a conversation at lunch with Martin and Elena. But first, I should mention, one of the disadvantages of genes, aside from requiring a large number of stars for the binning, is, of course, that you're assuming equilibrium, right? And so, related to that, Elena has looked at the effect of what you get for the Orth limit when you use the genes approximation versus the true density in an interacting simulation. So that's in the vertical direction. But it would be also interesting to see what are the discrepancies in the radial direction as well when you use genes versus looking at an interacting simulation, for example.
Yes, I agree. That would be interesting to look at.
Oh, sorry.
I guess Marla has a question.
Oh, hey. Hey, Juan.
Hello.
Great talk. So I have a question. So for genes modeling, you're stressing the con of the method as needing to bin. But in your previous work, you've used genes modeling on individual stars, so like not binning the actual data. And so my question is, is it better for me to think about genes as, because it's a moment method and that being the con of the method rather than the actual binning of the data? Or are those like the same thing?
So yes, even though Adrian disagrees, you can do genes modeling without binning. So I think mainly the con of it is that you have to assume an equilibrium, and that's definitely not true in almost everything that we look at. But in this implementation, it's the binning. In other implementations is the assumptions you have to make in order to not bin.
Okay, I need to think about that more. Thanks.
I don't know how it is that you do 4 weeks of work and then have too much for your talks, but this seems to be sort of a problem across the board. So I was thinking, oh my gosh, through the whole talk, the thing is, what if it's not in equilibrium? What if something, because that's all that I think about all the time is that things are not in equilibrium. Of course, you stuck that in right at the end. But I wanted to ask you, of all these techniques, if you have something out of equilibrium, which is kind of what we have, right? What would be the best technique you would think to pick out of your long stack?
I think it would ultimately be the Schwarzschild modeling, the very classical one, because that's already been shown to be robust to breaking equilibrium. But that's why I want to look at a simulation of dwarf galaxies and do the genes modeling at different points in time. And what I imagine is that at the very beginning, genes modeling won't work at all because you're very out of equilibrium. And then at some point, it works kind of well because you've done the phase mixing and have reached some sort of equilibrium. Not really, but more than before. And then if there's interaction, then you'll break genes modeling again. So yeah, I very much want to look into that.
I guess my first question was following up on Heidi is, when do you sleep? I don't understand how you could possibly have done all that work in 4 weeks, but there we go. So you clearly did. So question, yeah, maybe you can help with the intuition here. The extended Schwarzschild modeling. So I see Schwarzschild and I think orbits, which is what you talked about later. So what is the relationship between the two? I didn't quite intuitively.
Yeah, so let's get back to it. Break it. Okay, we'll get there. I wouldn't know which one it is exactly. Sorry, this is way too long. No, the one right after that.
Great, we get to see it again. There's so much stuff now.
Okay, so this top hat function in velocity position space is an annulus, right? So instead of I feel like it's gonna skip a lot. Okay, so that step function is just a ring around here, right? And so in the extended modeling technique, all I'm doing is saying there's a weight for some width here. And so it's almost exactly the same thing as weighing a bunch of orbits together. And that's pretty much what this is doing. So it's really doing the orbit library without needing to use an orbit library. No. I just calculate the action in my trial potential and then ask whether that action is in this step function or in this top hat function or this top hat function.
We are over time, but you haven't asked one yet, so go ahead, Elena, and then we will stop.
I want to go back to genes. I mean, I totally agree with Sukanya. We know that the disk or the Milky Way is out of equilibrium. However, if the perturbation of this state of equilibrium is not too strong, you can always use the perturbative theory.
Yes.
So.
And also, it depends on what question you're exactly asking, because the one thing that genes modeling does really well is an enclosed mass. It doesn't do really well with like what is the exact shape of the density distribution, but it can figure out masses pretty well. So even if it is slightly out of equilibrium, it should do pretty well at that.